G'day, my name is Mike Meakin, and today I will be describing to you a mathematical model that has been developed to allow the quantitative comparison of the autonomy of any two systems even executing dissimilar submissions. This presentation is based on a paper that has recently been submitted to the Journal for Unmanned Vehicle Systems. The agenda for today will cover a bit of background behind where the idea for this model originated, after which I will describe the main parameters of the model, discuss some observations that arose regarding the difference between executive autonomy and developmental autonomy, extend the model into the developmental regime, then provide a summary and conclusions followed by areas of potential further work. The genesis of the model occurred during a NATO meeting of unmanned systems industry engineers back in 2012. A spirited discussion arose between some attendees regarding the relative capability of various systems, but in the end the only thing that could be agreed was that autonomy just could not be properly measured. This made me think, why not? As Dr. Hare from UBC has noted, in order to advance a field, there must be a means of measuring the key parameters of that field. So if we want to advance autonomous systems, we need a way to reliably measure their autonomy. The leading model then and now is the Contextual Autonomous Capability Model, which is more commonly referred to as the ALPHUS model for autonomy levels for unmanned systems, defined by the National Institute of Science and Technology. This model proposes three key parameters or axes against which systems are evaluated, with descriptions for each axis. However, the evaluation is still really qualitative. Some of the problems with ALPHUS are that, being qualitative, the scoring against the three parameters is debatable and not reliably repeatable. There is no reliable means of distinguishing systems that fall within a single scoring range. The three axes themselves are not truly orthogonal, and the model is not designed to be applied to humans in order to compare systems performance to human performance. Recognizing these problems, we determined to revisit ALPHUS to modify, correct, and extend it to address as many of these deficiencies as possible. So we will now present to you the System-Agnostic Quantification of Autonomy Levels, or SQUAL, model, which will allow us to assess and compare the autonomous performance of systems across different missions, including the ability to compare humans to systems and even the ability to compare systems which include human operators as part of the overall system. And by doing so, we propose that this will provide the field of autonomous systems an important tool to allow the comparison of different algorithms, techniques, and systems in order to better advance autonomous system technology. Looking at the first axis of ALPHUS, human independence, we can see that other than renaming it to allow it to be applied to humans in the performance of a task, this parameter makes sense. Autonomy is clearly related to how much interaction the system needs with a supervisor in the performance of its tasks. Therefore, defining some ratio between the number of commands needed by the system to the number of decisions made by the system clearly has some relevance to how autonomous the system must be. But how do we do this? Since one of our guiding principles in the development of this model is that it should be able to be applied to humans as well as machines, we need to define the decisions made by a system in a manner that does not require insight into the inner workings of the system. So we define decisions to be an externally detectable change of state of the system with respect to the environment. So a change of direction of travel clearly reflects a decision made by the system. However, the movement of feet or the use of actuators to simply continue the direction of travel is not considered to reflect a decision by the system. So that means we have the behavioral independence level, or BIL, defined to be a function of the difference between how many changes of state of the system with respect to the environment are made against the number of supervisory interactions required, all normalized by the total number of change of state of the system with respect to the environment. Since ALPHUS uses a scale from 0 to 10, we try to maintain consistency by defining the function as an exponential of 10. There is a multiplicative scaling factor, a, that would be applied to the exponential ratio in the general sense. But there does not appear to be any literature that would help us determine a likely value for a, so we set it to 1 and see how the function behaves. This results in a BIL value of 9, equating to a system that makes 22 decisions for each supervisor direction. And if we compare this to how a human performance may be assessed, this would seem to be the equivalent of a fairly high functioning subordinate, so an independence value of 9 out of 10 seems reasonable. Placing the various BIL values on a spectrum and mapping in some values and examples, we can see that we have a full range of systems from very basic all the way up to fully independent. Some regions of particular note are the region between 0 and 1, where multiple supervisor inputs are required to accomplish even a single change in state of the system with respect to its environment. We have called this remote manipulation. And the top level region, where we can see that a system will execute greater than 200 plus decisions for each single supervisory input, reflecting a very high degree of autonomy. The next alpha axis is mission complexity. Again, this makes sense, since the degree of supervisory interaction alone is not sufficient to define true autonomy. A rock being used as a paperweight requires only one supervisory input, placement, to accomplish its mission. However, the mission is so simple as to be trivial, so to categorize this as autonomy is really a stretch. Considerable research has been done in a number of areas with respect to quantifying complexity. However, all these areas assume some sort of insight into the internal state of the system being examined, which makes their application to human endeavors problematic. Since we want our model to apply to humans as well as systems, we must constrain ourselves to defining a measure of complexity in a manner that would be applied to human tasks. Therefore, once again, we need the tasks that make up a mission to be externally observable. We exclude any changes to the environment that are not a direct result of the system actions. This then makes the tasks of a mission the same as the environmental state changes we use to determine the bill. We therefore define a mission to be the minimal set of actions taken by any system under optimal conditions that results in achieving all objectives. This definition makes the mission both system and environment agnostic. Each change within the environment is defined as a task. Within the mission are sets of decision points, a subset of which explicitly define the mission objectives. We can now apply some systems engineering techniques to define missions, such as use case analysis, which will readily identify the set of tasks needing to be executed, as well as potential alternate tasks that may be needed depending on the outcome of specific decision points, or even sets of tasks that may need to be repeated some number of times. So we try to break out the complexity of a whole mission by defining a mission as being composed of a sequence of tasks that are separated by decision points which govern the execution of subsequent sequences of tasks. Decision points define options between alternate task sequences or repeating previous task sequences. This lets us remove task repetition from the complexity of a task sequence so that we can deal with it separately later. All mission objectives relate to a decision point, though not all decision points need be mission objectives. Note that this definition of decision points also allows us to easily support coordination of missions between systems, as the decisions point could be a check to see how the other systems have progressed and selecting the next task sequence accordingly. Finally, this approach also isolates the complexity of parallelism to be solely within a task sequence. Sequences themselves will only be executed serially. So, a sequence is now any set of changes in environmental state that needs to be grouped together. This includes tasks that precede a decision point, tasks that come after a decision point, and any set of tasks that are or may be repeated more than once. The simplest mission would have one sequence of tasks, culminating in a decision point that was the objective of the mission. An example of a mission with 3 task sequences. Sequence 1 is the simplest, just a series of sequential tasks. Sequence 2 has 3 tasks in parallel with 2 other tasks for the entire duration of the first 3 tasks. Sequence 3 has parallelism for part of one task, so we could expect it to have less complexity than sequence 2. Now, within a task sequence, if we can assume each task has a complexity, which maps to cognitive load for a human, for each unit of time, then we can sum up the sequence complexity by just adding the complexity across all tasks for the whole duration. In theory, parallel tasks would just have contributions from all of the tasks being executed within a unit of time. However, we know that for humans, parallel tasks should have a complexity or cognitive load greater than the sum of the tasks if they were executed serially. So we end up defining an equation for sequence complexity that sums the weight or cognitive load of each task that is being executed within each unit of time, and sums that all across the duration of the sequence. In addition, we introduce an exponential multiplier, p, that increases the total sum of tasks being executed in parallel by a value exponentially proportional to the number of tasks being executed simultaneously. We'll see how this is applied shortly. We've already noted that we are using the term complexity as equivalent to cognitive load for a human. So ideally, we'd like to have an actual measure of cognitive load on humans of all of the simple tasks, such as take a step forward, that make up our task sequence. However, since this is a relative model, we assert that so long as both systems and both missions are evaluated against a common scale, then even if that scale has been defined by an individual's estimate of the relative cognitive load of the tasks, then the resulting comparison of the systems is still reasonable. What about the value of P, which increases the difficulty for the tasks performed in parallel? Again, we'd like real research to identify how best to define this function for a baseline human. However, if we arbitrarily set it to 2 and examine how it behaves, the behavior does not seem inconsistent with experience. It should be noted that P may be more complicated than simply a value. It may change depending on the types or similarity of the tasks being paralleled. So let's perform a sanity check on sequence complexity using juggling. Assume juggling a single orange has cognitive load defined as 1. Assume juggling an operating chainsaw is 10 times more difficult from the perspective of cognitive load. And let's use a value of 2 for P to capture the increased difficulty associated with doing tasks in parallel. With this, we find that juggling one orange has a complexity of 1. Juggling 2 oranges has a complexity of 4. And juggling 3 oranges has a complexity of 12. Since most people can juggle 2 oranges, but most cannot juggle 3, this does not seem unreasonable. Likewise for juggling chainsaws, the complexity is 10 times higher for each variation. Most people cannot juggle a single chainsaw, so its values of 10 in comparison to 12 for juggling of 3 oranges also seems reasonable. This seems reasonable so far. But now let's consider what happens if we juggle one chainsaw with 2 oranges. The complexity then is 48, so way more than for 3 oranges, and also more than for 2 chainsaws, but a lot less difficult than 3 chainsaws. This does not seem out to lunch. For mission complexity, we could expect that it should be just the sum of the complexity of all constituent task sequences. Which specific task sequences are executed in a given mission would be a function of the result of the decision points between the sequences. So it is proposed that mission complexity should include the complexity of all the potential task sequences, even those which do not end up being executed. However, recall that we had explicitly removed the complexity related to repeating of task sequences from the sequences themselves, so we need to capture that in the mission complexity. Clearly, repeating a sequence must be greater complexity than only executing it once. However, again drawing on the human experience, we know that repeated repetition results in a decrease of difficulty or cognitive load, so our mission complexity should reflect this behavior. We choose an asymptotically decreasing function to ensure both that the increase of complexity decreases with repetition and to allow us to calculate the mission complexity even in those cases where the number of repetitions is potentially unknown. So for the mission complexity, we sum the complexity of all the sequences and we sum the complexity of the repeated sequences multiplied by the inverse factorial of the number of repetitions to give us the behavior we have identified. Substituting in the definition of sequence complexity, we have the full equation. Note that there has been research done on specific learning curves for humans, AI, and machine learning algorithms, so some of these may prove better suited than our inverse factorial estimate. However, none of them directly relate to cognitive load, so it is not clear they meet our needs. So, returning to our juggling example, we can now examine how the repetition of the task sequence contributes to the overall complexity of the mission. Increasing the repetition from 2 to 4 cycles, we see that the increase in overall mission complexity is much less than the contribution of the first 2 cycles. Due to the asymptotic nature of the inverse factorial multiplier, we can place an upper limit on the mission complexity for the juggler, regardless of for how long he may juggle. So here is an example of a mission with 4 task sequences, only 3 of which would ever be executed. However, the mission complexity would include the complexity of all 4 sequences, including any potential repetition. The final axis in the ALPHUS model is environmental complexity, and this is the one that is problematic. Examination of this parameter makes it pretty clear that it is not truly an orthogonal axis, and NIST itself recognizes this in their ALPHUS document. So what should we really be measuring here? Again, examining how humans perform, we realize that if 2 people are performing the same mission, but one needs more guidance when something unexpected occurs, then we consider the one who needs less guidance to be more autonomous, and we say it is due to their initiative. So what is initiative, and how could we measure it? Again, examining what is involved with initiative, it becomes clear fairly quickly that initiative is the ability for the person to replan their mission as a result of the unexpected event, and to do so in a manner that still supports the mission objectives. So initiative can be defined as the ability for a system itself to replan some portion of the mission. Since we have already defined a method by which we can calculate the complexity of a mission plan, we can reuse this method to likewise calculate the complexity of the portion of the mission that has been replanned. We have called this parameter the initiatory complexity, and it is identical in form to mission complexity, but is instead used to quantify the most complex replanning that the system can support. So we now have 3 genuinely orthogonal axes defined that will allow us to quantify the autonomy of a system during the execution of a mission, and the ability of this system to remain autonomous in the face of the unexpected is captured within the initiatory complexity parameter. However, it is completely possible that this initiative could simply be the result of an exhausted set of contingency actions pre-programmed into a system. Is this still autonomy? The answer is maybe. For many applications, the user simply wants the system to be self-tending, and how it accomplishes that is immaterial. But for others, the user will want the ability to expand the set of supported missions without radical changes to the system itself. So this leads us to recognize that there are 2 domains of autonomy: executive autonomy and developmental autonomy, with the latter describing how much interaction is required with the system to increase its supported set of missions and the associated initiative for those missions. Providing a new mission set to a system should simply consist of providing a new course of actions. The real crux of the problem is developing the system initiative for those new missions. So we define the process that will increase the system's initiative within the new mission domain as a developmental process. At the lowest level, this is rewriting the system's code. For a more capable system, including humans, this is more of a training regime. So we need to define the complexity of the developmental process, very similar to how we define the mission complexity. The key difference, though, is how we handle repetition of developmental task sequences. Ideally, a highly capable system needs to be only shown how to do something once and it will be able to do it. If it requires seeing or doing it more than once, then this represents a less capable system, so we do not want to apply the asymptotic function to these repetitions like we did in the mission complexity. Therefore, leveraging the mission complexity definition, but removing the asymptotic function for repetition, we have this definition for developmental complexity. Often this can be further simplified since training is often executed in a strictly serialized manner and consists of only a single set of tasks. Likewise, we can repurpose the definition for build to capture how much developer or trainer interaction is required for the system to reach the required degree of initiatory complexity in the new mission domain. We can see from this DIL chart that we once again have a spectrum from complete recoding through training to self-training and self-realization. In summary, we have described the SQUAL model that extends and modifies the existing ALPHUS model from NIST. The SQUAL model supports the ability to quantifiably assess the autonomy of any system for comparison in a relative sense to any other system, even if they are performing dissimilar missions. The model provides a means of comparing systems for anyone in the autonomous systems field. And this ability should enable the autonomous system community to better advance the technology by allowing identification of the strengths and weaknesses of each system. This is a list of specific areas for further work that would be beneficial for the application of the squall model. The first being the development of a baseline set of simple tasks that could be expected to make up any mission. This would ideally be developed by direct measurement of cognitive load across a statistical population of people in order to define a baseline human with explicit cognitive load values for an extensive set of simple tasks such as advance forward 1 step, turn 90 degrees, grasp an object, move an object, place an object, check for collision risks, move at high speed, etc. The ability to define an accurate cognitive load curve that reflects the reduction of cognitive load on a baseline human as a result of repeating tasks would be directly useful. The ability to determine and define the function P that captures the increased cognitive load on a baseline human as a result of executing specific tasks in parallel. It seems likely that this would be a function of task type and not just a hard value across all tasks. Even in the absence of the first three inputs from the cognitive research community, use of the squall model for comparison of different systems across dissimilar missions could still be effective so long as the systems and missions were evaluated against a common and reasonable, based on experience, set of assumed cognitive load values. Since the squall model is inherently relative, this would result in the values being incorrect when compared to the yet-to-be-defined baseline human, but would still be of value in comparing the systems within this common set of definitions. Adoption of the squall model as an evaluation mechanism by procurement agencies would both facilitate more consistent and defensible procurement decisions and also encourage the adoption of quantitative measurement, assessment, and improvement by the industry as a whole. Utilization of the squall model to assess human-machine interfaces would be achieved by treating the human-machine combination as a system under evaluation. This approach might be of particular use in assessing the intuitiveness of the HMI, as that should be reflected in the evaluated initiatory complexity of the system as a whole. Better HMI would be expected to result in better performance against unexpected events. The plane described by the bill and mission complexity parameters should effectively equate to HMI usability, with greater mission complexity value and lesser bill values defining an improved interface. Finally, utilization of the squall model can be envisioned for use in evaluation of human training programs by directly capturing the complexity of the training program that needs to be implemented and the degree of interaction required from a trainer to achieve greater competency and initiative in the targeted mission domain. Reducing the DIL and the DC while maximizing the resulting initiatory complexity across a population of trainees would represent the ideal solution for an organization. Optimizing for reduced DIL, even at the cost of increased DC, would represent an opportunity to move the training to be self-directed. Thank you very much. I am now available for questions.